On November 15th, 15 days of darkness will begin. Jupiter and Venus will move closer to each other than ever before. Venus will be to the southwest of Jupiter and shining 10 times brighter than the gas giant. This will heat up Jupiter's gases, causing a huge amount of hydrogen to surge into space. The hydrogen will collide with our Sun on November 15th, causing a massive explosion. The Sun's temperature will increase by 9,000 degrees, turning the star blue. As a result, the Sun's light will be much dimmer, and it will need at least 2 weeks to return to normal. Earth will experience a 6 to 8 degree rise in temperature during the blackout. Former head of NASA Charles Bolden says, "No one should worry too much. This event would be similar to what Alaskans experience in winter."
Hi, I'm Jason.
I'm Sarah.
And I'm Catherine. Welcome to Castor in the Classroom's Stories from Sydney Observatory.
Well, according to the internet, we've only got a short amount of time left before the light goes out. The sun, that is.
Well, we've better get on with it then. Over about the next half hour, we're going to be talking to you a little bit about some new and old ideas about our solar system. We'll be showing you some of the telescopes here at Sydney Observatory and then trying to figure out whether or not for the next 14 days or so we are actually going to go into darkness.
See, science is all about sorting the fake news from the real stuff. So you guys can ask questions throughout the session today. If you're signed into your Google account, you could send in some live chats, or you can tweet us using the hashtag on your screen, hashtag CITCOBS, or tagging us at CITCVC.
But before we can understand what we know and how we know it, we really need to learn a little bit about what an observatory actually is and how an observatory helps us learn more about our solar system.
So it's just a place where we can actually make observations of the sky, isn't it, Sarah?
Yeah, exactly. So the observatory is the building itself that houses a number of different telescopes, and those allow us to make observations of objects in the sky.
So shouldn't we be here at night time then?
Yeah, perhaps we should. So Sydney Observatory's telescopes are optical telescopes. That means that they collect the same light that your eyes see. So during the day, we can't really see anything useful. That's because the sun's light comes in, it bounces around our atmosphere and makes the sky appear brighter than any of the stars in the sky. Those stars are still there, of course, we just can't see them until the sun sets.
People have been observing the sky for basically as long as we've been around, but until recently we were only ever using our eyes. We didn't have really great instruments like this telescope here that could really aid our observations. But for the past 50,000 years, do you guys think the skies looked exactly the same?
Yeah, pretty similar actually to how it looks today. Not exactly, but pretty close. Each of the stars in the sky are on their own path around our galaxy, but it would take a really, really long time, much more than 50,000 years, to see any significant change in the patterns of the constellations. Having said that, from time to time, some pretty spectacular things can happen, like a supernova, which is where a star explodes. The last time this happened, and we were able to see it with the naked eye, was in 1987. A supernova went off in the galaxy called the Large Magellanic Cloud. It's a nearby dwarf galaxy. But astronomers think that a star in the constellation of Cygnus is actually going to go supernova between around 2021 and 2023, which is pretty exciting, I think.
Indeed. So that's a really cool link to the past, and the fact that so many things are going on Earth and so many things change so quickly here on Earth, and yet the sky stays pretty much the same for really long periods of time, as does our fascination with them.
In fact, the first person that really used a telescope to observe the stars was an Italian mathematician. The telescope was around a 20 times magnification. Now, that was pretty good because it actually allowed him to observe the 4 largest moons of Jupiter for the very first time. Now, that actually completely dispelled the current model at that time for our solar system, that everything was orbiting around the Earth. Now, not only did he manage to observe the 4 moons of Jupiter, but he also was able to see the phases of Venus. He also detected the great red spot on the surface of Jupiter, which is a storm that still rages on the surface of Jupiter at the moment. He even managed to observe the rings of Saturn, which he called the Saturn's ears, just because it looked like that through his telescope. But unfortunately, the Roman Inquisition found him guilty of heresy, and he was trialed, and he was found to be believing in the heliocentric model of the solar system.
So the heliocentric model is the idea that the sun is at the centre of the solar system rather than the Earth and the other planets orbit around it. Now, Nicholas Copernicus was the first person to mathematically explain the heliocentric model and to try to actually use it to predict the motions of the stars and planets in the sky. Having said that, he wasn't the first person to come up with this idea. He was actually inspired by ancient astronomers all throughout history, from the ancient Greeks to Islamic astronomers and many more. But for a long period of time, as you said, this geocentric model, it was the dominant model of the solar system. So that's where the Earth is at the centre. We now know that that's impossible because the Earth weighs much less than the Sun does, so its gravitational field couldn't possibly be strong enough to hold the Sun in orbit around it. But that didn't really help Galileo when the Church, at a time that the Church was supporting the geocentric model.
What would you guys have done if you were in Galileo's spot? Would you have continued fighting for something that you knew was true, or would you have denied it and believed in something that you knew was false just to avoid arrest? Well, Galileo tried to deny that he believed in the heliocentric model, but unfortunately it was a bit too late and no one really believed him, and he had to spend out the rest of his days under house arrest.
So Galileo could only really see things that were visible with the eye and through his telescope. The amazing thing about some of the modern telescopes we have nowadays is we can see things that are ordinarily invisible to us. So, and even to, modern optical telescopes like this one here behind us. Now, these types of telescopes observe radiation like X-rays and gamma rays, and even radio waves. So this is light with different energies, essentially. So the atmosphere does block and distort some of these energies. And so what astronomers have done to try to fix this problem is we actually put some of these telescopes up into space. Now, possibly the most famous of these space telescopes is the Hubble Space Telescope. But there's a whole fleet of space telescopes up there, including Kepler, Planck, Gaia, WISE and Fermi, just to name a few.
That's pretty cool. But back when the observatory here was built, the idea of putting telescopes in space would have seemed like a pretty mad idea, don't you reckon? But one person who knows more about this observatory than just about anyone else is curator Dr. Andrew Jacob. Andrew, thank you so much for being with us today.
Thank you, how are you?
I'm fantastic. Can you please tell us, why was this observatory here built?
The observatory was built in this place in Sydney about 159 years ago, almost 160 years ago. But we have our 160th anniversary, in fact, next year. So back in 1858, the observatory was built here with a very tall tower. And on top of the tower is a large yellow ball. And that yellow ball rises to the top of the mast and drops at precisely 1 o'clock. So it tells everybody the time. We know exactly when 1 o'clock is each day. But how do we work out the time? We don't have a watch. Back then we had clocks, but we needed to set them somehow. So what we did with the astronomer would look through a very special telescope which was pointing up to the north. And as the sun came across the sky, it moved over the end of that telescope, and we knew that the sun was due north because the telescope was pointing due north, and we knew that was midday. So we could work out when midday was by the position of the sun as it travelled across the sky. Okay. And then we could drop the time ball at precisely 1 o'clock.
Oh, fantastic. So why was this particular location chosen then?
The observatory was put right here because this site is the highest point in the city. It sits on top of the hill. Back then there's no harbour bridge, there are no city buildings. These days if you look at the city you can't hardly see the observatory. It's swamped by all these concrete buildings. But in the past it sat up on top of the hill proud of everything, and everybody around the city could see it. So they could see that time ball really clearly. Oh. But most importantly, the ships in the harbour could see it. So the ships would look up and they would see the time ball drop. They would be able to drop their they would be able to check their chronometer against the time ball dropping. And I think you can see a little bit of footage about this happening at the moment. Okay. And they would check the time of their chronometers every day that their ship was in port. So they would know whether their clocks, their chronometers on board their ship were running well or not. After that, a little bit complicated, they could use their clocks to work out their position on the oceans around the world. So the observatory is here on top of the hill, so it could be seen by all those ships and let them navigate safely and get to their destination.
Oh, well, that makes a lot of sense. So as you said, this observatory has been here for a long time, almost 160 years. So does that make it the first observatory in Australia?
It wasn't quite the first, no. There was actually a small observatory that was set up by Lieutenant Dawes. He was here aboard the first fleet that arrived from Europe in 1788. And he set up a small observatory just down where the Harbour Bridge pylon is now. It doesn't exist anymore. He did some weather observations. He looked for a comet but didn't find it. And he did look at the stars and planets. So his observatory lasted while he was here, just for a few years, and that ended up falling over probably. It wasn't used after that. A little later on, about the 1820s, the Governor of New South Wales, Governor Brisbane, arrived, and he was quite a wealthy man. He paid for his own observatory, had an observatory built out at Parramatta near his house. He paid for 2 astronomers to work for him, and he paid for a lot of instruments, telescopes and clocks and other instruments he could measure the positions of stars with. So that was the second observatory. Now that one did crumble. That was eaten by white ant over the years. It lasted for about 30 or 40 years, but finally it was eaten by white ant. Although if you go out to Parramatta now, just near Old Government House in the park beside Parramatta, you can see 2 sandstone pillars on which one of the telescopes sat. The other instruments that Governor Brisbane had came here to Sydney Observatory. So we were the third permanent observatory in Australia. And we still remain. So in 1858, the observatory was built in solid sandstone, and it's lasted ever since.
That's fantastic. So we've heard a little bit about how the observatory here was used for timekeeping, but can you tell us a little bit about the astronomical background of the observatory and the different telescopes that it's housed over time?
Yeah, so I hadn't really mentioned astronomy because back then, observatories weren't really used primarily for astronomy. Their main job was much more practical, to help people know the time, to help ships navigate, to measure the weather and record the weather and make predictions about the weather. So astronomy was there. You needed an astronomer to look for the sun to tell the time. And given that the astronomer was mainly doing his work in the middle of the day, fortunately the government gave him a lovely large telescope, and we've still got that, a beautiful 29 centimetre diameter telescope in our South Dome, a beautiful refracting telescope. And he used that to look at the stars and planets. He looked at a few things. He looked at Venus travelling across the face of the sun. They took some photography of parts of the southern sky. They were doing that sort of work. That's the nice historical telescope in the South Dome. There was the transit instrument, the transit telescope, which is the one that looked for the position of the sun. We've still got that here, and we still use that. And as I mentioned, the Brisbane instruments, Governor Brisbane's instruments from Parramatta Observatory, we've got those, but we don't use that telescope anymore. That's a very small one. It's very, very fragile, so we keep that in the collection locked away.
Understandable. So, of all of these things that the observatory did, what would you say was the most important astronomical work?
What was the most important astronomical work we did at the observatory? There are quite a few. Perhaps 2 stand out, however, over the 160-year history of the observatory. One would be the transit of Venus. In about twice a century over the millennia, Venus appears to cross the face of the sun. Appears as a little black dot moving across the face of the sun. And if you use the right equipment and make sure you're safe, then you can observe that happening. And if you observe that movement of Venus across the face of the sun from different parts of the Earth, then you can use a little bit of simple trigonometry, and you can work out the distance between the Earth and the sun. Now that's pretty clever. You are sitting on the Earth looking at something in space with a telescope. You don't have a ruler, you don't have a big long piece of string, you've just got images of the sun and Venus moving across it, and yet you can work out the distance between here and the sun. And that was a really important thing to measure back then. It didn't help anyone in their daily lives, didn't help them get a better meal or go to work quick or anything like that. But it was an interesting thing to know for science, just what was the distance to the sun. Yeah. So the transit of Venus helped us find that distance.
Quite amazing.
That was pretty important. Yeah, it's very, very clever. And I guess the other thing would have been the astrographic catalogue. There was, in the mid-1800s, 1850s, 1860s, the technology of photography came into being. People developed that and made it work properly. And these days you just pick up your phone and you take a snapshot. You can take as many snapshots as you like. But back in the past, photography was the way things done, and it was brand new back then, like phones are these days, like mobile phones are these days. And so, as you can see on the screen, they took these beautiful astrographic catalogue plates. These are glass plates with a chemical coating on them which records the image that you can see. And they recorded the entire sky. It was a project that was done by observatories all around the world. We had a section of the southern sky that we took, and this image shows you those stars, some of them that we took. And there's probably 2,000, maybe 3,000 stars on this glass plate. And a lot of women, it was only women back then, not men, they weren't given the job. The women would sit down, look through a microscope and measure the position of every single star in every little grid square that you can see on that photograph.
That's incredible.
And
That must have taken a really long time.
It took a long, long time. So the photographs, most of the images and photographs plates, they were taken back in the 1890s into the 1920s, a long time ago. But they didn't finish doing the work until about 1964. So it was a big, long project, and the observatory still has all those glass plates. We have the telescope that was used for taking those photographs. We got all the information, all the details. It's a wonderful collection that we have.
Yeah, wonderful. Okay, well that's been so interesting to learn about the history of the observatory and the astronomy and the timekeeping work that it did. Thank you so much for being with us today, Andrew. It's been really fascinating.
Thank you. Enjoy your morning.
Thanks, Andrew.
So, just reminding everyone out there in their classrooms that you can ask questions throughout the feed, so just keep those coming in. So we're here, as we mentioned, in the East Dome of Sydney Observatory with what is obviously a pretty modern telescope. Andrew mentioned the South Dome telescope, housed in the main building of the observatory, houses a refracting telescope that, as he said, was used to observe the transit of Venus, where Venus passes across the face of the sun in 1874.
Yes, so a refracting telescope is pretty much the same type of telescope as Galileo actually used when he was observing Jupiter and Saturn. And so what we can actually do is we can actually create one of these pretty easily. So to do this, all we need are really 2 lenses and 2 pieces of cardboard tube of different diameter. So these lenses are different thicknesses. We've got a thinner lens, which is what we use as the eyepiece lens, and the thicker lens, which we use as the objective lens. So what happens is we place these inside a cardboard tube, much like this, and then what we can do is we've got the eyepiece in one end, the objective in the other, and we point it towards the object we want to look at. Now, whenever you're using one of these, please keep in mind not to point it at anything too bright. The last thing we want to do is point it at the sun or something really bright, because it could damage our eyes. It is, after all, focusing this light onto the back of our eyes, onto the retina. So what we do is we look through from one end, we change the distance that the tubes are apart, and we look through it, and that focuses the light. So the light comes through the first lens, through the objective lens, is bent or refracted, passes through the telescope, and is bent or refracted once again as it comes out of the eyepiece lens. It then focuses onto the back of our eye, or the retina, and so that's how we can use these telescopes to actually look at things in the sky. Now, this type of telescope will probably magnify objects by about 10 times.
There's also reflecting telescopes. Now, that's a little bit different to the refracting telescopes, because instead of 2 lenses, it uses 2 mirrors and a lens. So in a reflecting telescope, the primary mirror, which is roughly here on this telescope, was what collects all the light of what we're observing. It's then reflected up into the secondary mirror up here, and then reflected back down into the eyepiece. And as Jason said, it then focuses the image on the back of your eye in the retina. And that's how it's slightly different to a refracting telescope, because it reflects the light instead. Now, refracting telescopes do provide a steadier image of the object, but they are a little bit more expensive to produce. They're really easy to maintain though, but producing large-scale refracting telescopes is really not the way to go. Reflecting telescopes, on the other hand, are much easier to produce from the large scale, and they're much cheaper to produce, which means that today pretty much most of our research telescopes are reflecting telescopes, not refracting.
Exactly. So often the best place to place telescopes is actually in space. But it's really expensive to launch these telescopes and put them up there. And not only that, if it gets damaged, it's really difficult to fix. You can't just call up the repairman and get him to pop up into outer space. So where is the best place to put one of these telescopes, Sarah, on Earth?
So if you're building it on Earth, you want to put your telescope in a remote place so that you're away from the bright city lights and the light pollution that causes. And ideally you want to put it up somewhere high so that the effects of the Earth's atmosphere are minimized.
So Sydney City, probably not the best place for an observatory.
No, you have to remember it was a lot darker in the past, but nowadays it's not the greatest location to view the sky from. You've probably noticed if you've ever been out into the country, how many more stars you can see from the country than you can from the city, so that's why.
And we're not very high up, are we, Sarah?
No, we're on a hill, but we're not at altitude. So the problem with that is we're looking through a lot of the Earth's atmosphere, and especially with the pollution and light pollution added, that distorts the light coming from the stars and means we don't get as clear an image as we would like to. But having said that, you can still get a fantastic view of lots of objects through the telescopes here at Sydney Observatory. Things like the moon, our nearest astronomical object, and many of the planets in the sky will look spectacular.
So telescopes have helped us learn a little bit, or actually quite a lot, about what our solar system looks like. So we'd like to just bring Andrew back in for a moment. Andrew, how much of the solar system can we actually see from here in Sydney?
We can see large parts of the solar system. So let's work our way through it. Clearly we can see the sun, which we know is at the centre of the solar system, and we use the right equipment to safely look at that. We can see the planets that you can see with your naked eye. So they would be Mercury and Venus. Earth doesn't really count because we can see it anyway. Mars, Jupiter and Saturn. Those 5 planets have always been visible to the naked eye. We don't know who discovered them because humans have been able to see them ever since humans looked up in the sky. We can of course see the moon as well. Now the moon used to be called a planet, but we now know that it's a moon orbiting around the Earth. So those are the bright things. I think it's not a surprise that we can see those, even from Sydney where it's bright. We can also see Uranus and Neptune, the last 2 major planets, with our telescopes. Now theoretically you can see Uranus with your naked eye, but it's right on the limit of vision. It's about the faintest thing you can see by eye, if you know exactly where to look. But most people don't, and I don't know where to look, so I use the telescope to find it, much easier. And this brings me to the next point that's probably important in answering what can we see. It's not how far away the object is or how big it is, it's how bright it is or how faint it is. So we can see things that are bright, and as they get fainter and fainter and fainter, at some point they're too faint for us to see. So Uranus is really too faint for most of us to see by eye. Neptune is definitely too faint to see by eye, but it can be seen by telescope. This is because the telescope has a bigger diameter than your eye does. Your eye's diameter is tiny, even at night time when your pupil opens up. So it only gets a certain amount of light into it. And you can see the telescope behind us is enormous, so it can collect much more light, like a big bucket collecting rain. And so it can see fainter things. What is there? We've got Pluto. So Pluto is not a major planet anymore, it's one of the dwarf planets, and there are a handful of dwarf planets. With this telescope, however, we can't just look through this telescope and see Pluto. Pluto is so faint, even this telescope doesn't collect enough light to see Pluto. We could record the light over a long period of time, like they did with the Astrographic Catalogue project. We could record it on a camera of some kind, and we could see it. Or we could use a bigger telescope. Maybe a telescope twice the diameter of this might be able to see Pluto. And what else is in the solar system? Name some other things in the solar system for me.
Comets, asteroids.
Asteroids, perfect. So we can see comets if we can see them by eye. Very rarely, maybe once every 20 years, there's a nice bright comet that appears in the sky and you can view that by your naked eye. That's really great. We haven't had one for about 15 years, so we're almost due for another good one. I'd love to see another one. They're usually really spectacular. Many of them, though, are too faint to see by eye, but you can see them through the telescope.
Oh, excellent.
And then asteroids. Now, there's 2 or 3 asteroids which are just bright enough to see through our telescope. And I've been very lucky. About a month ago, I saw one of those, and it was just moving steadily through the eyepiece. Not many people get the chance to see that. You've got to be in the right time, at the right place, and have the right telescope to be able to see that. So that's kind of cool. So that makes up most of the solar system. The planets, moons, we can see moons of Jupiter and Saturn, of course. Comets and asteroids, those are the things that are in the solar system. Most of those we can see either by eye or with the help of the telescope.
So that sounds amazing. So those are the things inside our solar system. What about outside of our solar system? You said we can look at really faint objects with larger telescopes. Can we see things that are outside of our solar system?
Well, yes, we can. And you always see things outside the solar system. Our solar system is the sun plus the planets and some comets and asteroids. When you look up in the sky, you see stars as well. And the stars are all outside our solar system. And if you look very carefully in just the right spot of the sky, you can see outside our Milky Way galaxy as well. So the stars you see are part of the Milky Way galaxy, a big spiral structure in space. It takes a long, long time to travel across the... You need Star Wars technology and hyperspace to get across the galaxy. It doesn't work otherwise. But beyond that, there are a few galaxies elsewhere in the universe. Well, there's billions of galaxies in the universe, where we can see about 3 of them with our own eyes. And again, it depends on how faint things are. So with your eyes in the nighttime sky, if you go out in the nighttime sky, even from the city, you might see a few hundred stars. If you're lucky enough to be in a countryside where it's perfectly dark at night, then you would see perhaps 5,000 stars in the sky. You try counting them one day. Don't do that. It takes too long. If you use a telescope like this one behind us, you could see maybe 1 million stars, perhaps 2 million stars in the sky.
That's incredible.
Which is incredible. But in our Milky Way galaxy, there are about 100,000 million stars.
Wow.
And I don't know what 100,000 million looks like. But people tell me that if you go to a beach and you start counting the grains of sand on a beach, you won't reach a 100,000 million number of grains of sand. So that's a lot of stars, more stars than there are grains of sand on the beach.
It's incredible.
And we only see maybe 5,000 of them with our own eyes. And then beyond that, all the other galaxies, the gas clouds where stars are being made, the black holes colliding, which we need special telescopes to detect, all sorts of things out there. So we can see a lot of those things from our observatory, but not everything.
Wonderful. Thanks again, Andrew.
Thank you.
Well, guys, it's about 10 o'clock at the moment, which means we only have a few hours left. But before we worry about the darkness that's going to sweep over our Earth, we've got a question from Wanissa School, which says, how many planets are in our solar system? So, do you want to answer that one?
Sure. So we have about 8, well, actually we have exactly 8 planets in our solar system. Some of us grew up with Pluto being a planet. However, as we've just heard from Andrew, Pluto is now what we call a dwarf planet. So we have 8 planets going through from Mercury at the closest all the way out to Uranus at the end. Sorry, Neptune at the end. Thanks, Sarah. We do also have some dwarf planets. We've got about 6 dwarf planets, I believe, at the last time I
There are
checked.
5 named dwarf planets, but we suspect that that number is much larger, and that was part of the reason that Pluto got demoted, so to speak, is that we realised that there were many, many more Pluto-sized objects out there in our solar system, which could potentially be dwarf planets. No, that wouldn't be a fun exercise.
Way too many. There's also another question which says, why are the planets appearing to get fainter and fainter? And that's also from Wanissa High School.
Ah, okay. So I'm presuming that the reason that the planets appear to get fainter and fainter is that we are just getting surrounded by more and more light pollution. As we've heard from Andrew and we've mentioned a couple of times, the light pollution around us in the city particularly means that we can only see the brightest objects. We can't see the things that are dimmer. And so compared to the light pollution that is surrounding us, the planets will probably not appear as bright and as dominant in the sky as they once would have been. And the same would be true of stars and other objects that we can spot with our naked eye from the city.
But you guys can always go out into the country or away from the city lights and use a telescope of your own to try and find those planets and see for yourself what they look like out away from the city lights of Sydney.
And you only really need to go, what, about an hour and a half or 2 hours out of Sydney.
dramatic
Somewhere like the
improvement.
Blue Mountains will give you an impressive view of the sky.
Absolutely. So don't forget to keep sending in your questions, guys. Thank you so much for those ones. But let's have a look at this myth and see if it is a myth or are we actually going to be plunged into darkness for the next couple of weeks. So the first thing that this rumor claims is that Venus and Jupiter are going to be closer than ever before. So guys, is that true?
Not really. So while they're going to appear very close together in the sky, this is something we call a conjunction. So they'll appear close from Earth. They're not actually going to be close to one another in space at all. So the planets are orbiting around the Sun, as we've heard in the solar system. Venus is the second planet from the Sun. Jupiter is much further out. It's about 7.5 times further from the Sun than Venus is. So even when they appear close to one another in the sky from Earth, they're not actually near to each other at all in space.
Well, I guess that disproves that bit, but it also says that Venus is going to be shining 10 times brighter than Jupiter, which is going to heat up the hydrogen gas, causing a surge of gas into space, which will collide with our sun, causing a huge explosion.
It sounds dramatic, and although it's true that Venus is brighter, it appears brighter than Jupiter, it's certainly not going to cause that. So the reason that we see the planets in the first place is because they reflect the sun's light back at us. So they don't actually make their own light, none of the planets do. So Venus appears brighter than Jupiter for a number of reasons, one of which is just the fact that it's closer to the sun than Jupiter is.
So, however, the dark side of Venus, that is the side that is facing away from the sun, is the side that's actually facing towards Jupiter. So what that means is that the sunlight is being reflected away from Jupiter, not towards it.
But even if Venus were reflecting the sunlight towards Jupiter, it wouldn't actually make a difference. The distance between the planets is so great, and the amount of sunlight falling from Venus onto Jupiter would be so small that any change in temperature that it could have would be so tiny, so minuscule that we couldn't even measure it.
I guess that looks like you're saying no surge of gas, no giant explosion, which means there's going to be no change in the sun's brightness whatsoever?
Not at all. And by the way, the quote that we heard from NASA's Charles Bolden in the myth at the beginning, he never said that at all. It was completely made up.
Although I guess the rumor does bring up a really good point about colour and temperatures of stars and how colours are related to the temperature of the star. Is that true, guys?
Yeah, that's exactly right. So just like when you're cooking on your gas cooktop at home, you always want to cook on the blue flame. And the reason for that is because that blue flame is the hottest flame. So just like with that, when you look at blue stars, those stars appear to be bluer in colour because they're actually hotter, whereas the redder stars are actually cooler. Now, of course, when an astronomer tells you that a star is cooler than another star, it doesn't mean you actually want to go there and visit it. It's still several thousand degrees Celsius on the surface. So not exactly somewhere you would want to land.
Not a place for a holiday.
Definitely not. No. So that's good to hear, I guess. So are we basically going to say that is the Earth going to be plunged into darkness?
No.
No.
Because
Science
said
says so.
So thank you guys for chiming in for Sydney Observatory, stories from Sydney Observatory with Castro in the classroom. I'm Catherine.
I'm Jason.
I'm Sarah. Thank you.